Hello and welcome back to my channel. Today we're going to be talking about the applications of Newton's laws and how we can really apply them to some of the questions we have. So before we start, let's just do a little quick recap from the last video. So let's talk about Newton's first law. Newton's first law basically stated if an object does not have any external force on it, then it won't move, which basically means that all the forces are balanced. So if we have an object here in a full body diagram, there's no force on it. That means the force applied will be equal to the force of friction, and the force of normal will be the same as the force of gravity. Newton's second law implied that the net force on an object, which is the total amount of the forces, is equal to the mass times the acceleration. So force net is equal to mass times acceleration. The reason I'm going through this quickly is because I did an in-depth video about this previously. So if you want the full video, you can just go to the one previous to this. Newton's third law basically states, his final law is that all actions have a reactionary pair. Just like if you were to punch the wall, the reason your hand hurts is because however much force you punch it with is the same amount of force that you're getting back from the wall. So all actions have a reactionary pair. There's no unbalanced amount of forces. Every force has a pairing force that comes with it. So that's something to keep in mind when working through these problems, and will be crucial to really looking at what the problems that we have. So let's read the question and let's see what we have. So it says 3 sleds are tied together and pulled east across an icy surface with an applied force of 12 newtons east. The mass of the sled 1 is 12 kilograms, the mass of sled 2 is 11 kilograms, and the mass of sled 3 is 7 kilograms. Assume there is no friction. Okay, this question, there's a few things we have to take into consideration and to actually tackle what we're doing here. So the question that it asks is determine the acceleration on all the sleds. So let's first get our given down. So we know that, M1, so mass 1, will simply be 12 kilograms. M2 will be 11.0 kilograms. Pardon me, I forgot the 0.0 here. And mass 3 will be 7.0 kilograms. Remember, it actually gives us a direction, so we have to define our direction east to be positive. Now that we've done that, it seems as there's a typo in here. This should be 120 newtons because in the picture it says to be 120. So it says the force applied, so our FA is equal to 120 newtons. So now that we have all of this given down, we are required to find its acceleration on the sleds. So how are we going to find the acceleration? There's a few things we can take into consideration and something that we have to really keen in on to really make our decision. So the important part about this is that our acceleration on 1 will be equal to their acceleration on 2, which is equal to our acceleration just in total. Because if this sled is tied together with all these sleds and it's moving assuming that the rope has no bend or it doesn't pull, the same acceleration that this sled is moving at, all of these are following with it. So the acceleration will be the same from sled 1 to 2 to 3 because it's all being pulled by the same object, moving in the same direction. So we know that the acceleration 1 will be equal to acceleration 2, which is just equal to acceleration as a whole. Now that we understand that, let's get into our free body diagrams. So let's go into our analysis. Let's draw a free body diagram for our first object. So mass 1. So we have mass 1 right here. Pardon me. So we have mass 1 right here. And on mass 1, we have a force applied. We have a force of gravity, force normal. And we also have another force basically of tension technically because there's a rope attaching both of these sleds right here. So there's a force of tension, but we can refer to it as the force of 2 because this is the second sled, the force of 2 on 1 on the first object. It's the force of the second object on the first object. Now that we have this, we can draw our next free body diagram, which is for mass 2, M2. So M2 has this way, if we look back at the rope, there's a rope attaching these two again together. So there's a force of 1, the force of this object on this object, on 2, because they're pulling each other forward, right? And there's always no opposite amount of forces. So that if there's a force of 1 on 2, there's going to be a force of 2 on 1. And we also have, again, force of gravity, force normal. But because we're determining the acceleration, and there is really no, typically, there's no change in the y direction. It's all in the horizontal. We can really assume that we don't really need to keep drawing out force normal and force of gravity. Also for this question, it does say there is no friction. So if you're wondering, why don't we have a force of friction here, or why are we putting FF with the tension or the action-reaction pairs, it's because there is no friction involved in this question. So we know we have the force of 1 on 2 on object 2, the sled here. On the second sled, right on this sled right here, we have the force of 1 on object 2. And we also have another rope connecting this one to object 3. So we also have the force of 3 on 2. So the force that the object 3 puts on object 2. We also have those with it. Now let's draw a third free body diagram for our third object, so our M3. This object, it's only connected to, this object right here is typically only connected to object 1. So we know that the only force of this is going to be the force of 2 on 3. The force of object 2 on 3. And there's no other objects with it, so that's the only force that we have. Now that we have this, we can start to put in what our forces are and how this will really matter in the end. So we can put in the equation. So we know that force net, or net force, is going to be equal to the force applied plus the force of 2 on 1. Now we can use vectors, or what's important is we can interpret the direction. Because we set a direction as positive, we can set, because we set technically we set right as positive, therefore we can interpret the left side or west to be negative. And this helps because then we don't have to keep using our vector signs, and we can drop our vectors and just go into interpreting our direction. So we can also write this as force net is equal to force applied minus force of 2 on 1. Correct? Another key thing to notice about these forces are that action-reaction pairs are again equal to each other. So we can also put that here. We can put force of 2 on 3 is equal to force of 3 on 2. Force of 1 on 2 is equal to force of 2 on 1. Force of, they're all equal. So that's something to keep in mind. Why is this important? And how does that even make sense? Well, if you punch the wall, you're getting the same amount back. You get an equal amount of force in back that you put in. So in this case, when your action-reaction pairs are always going to be the exact same, force-wise. Why is that important? Well, we can go further into the question and we'll discuss. So now that we know this, we can draw the next. We can sub in our equation for force net. Force net is equal to m times a. So we can put mass times acceleration is equal to force applied minus force of 2 on 1. Now we can go into putting in our forces for object number 2. Our net force is equal to force applied plus force of 2 on 1. Now that we have that, we can interpret our direction, and we can go, you should put net force 1, 1, and then put mass 1. Make sure you keep your subscripts because it'll keep your work more organized. So net 2 is equal to, you should put force applied. You don't technically need to put force applied 1 because there's only one force applied, but sometimes it can help you see your work better. But force of net 2 is equal to force of 1 on 2, because we have that right here, minus force of 3 on 2. I did a typo here. This should have been force of 3 on 2. Now we interpreted our direction, and we know we set right as positive, so our force of 1 on 2 will be positive, and our force of 3 on 2 will be negative. And then we can just drop this vector sign, and we have F net. Now we can just sub in M2A is equal to force of 1 on 2 minus force of 3 on 2. For this last object down here, or this last mass, we only have one force acting on it. So we can put F3 net is just equal to force of 2 on 3. And we can just interpret our direction again. So F net 3 is equal to just force of 2 on 3. And now that we interpret that, we just put on mass 3A is just equal to force of 2 on 3. Now, why does this help, or why is this important? Well, like we talked about before, if the force of 2 on 3 is equal to the force of 3 on 2, and we know what the force of 2 on 3 is equal to, the force of 2 on 3 is equal to mass m3 times the acceleration, well, we can sub this right here up into this formula because we have force of 3 on 2 there, right? Because up here, we don't know the force of 1 on 2. We don't know the force of 3 on 2. We have too many unknowns. But we can just sub in this formula down here, up here, because force of 2 on 3 is equal to the force of 3 on 2. So let's sub that in. We can label this as number 1. We can label this as 2. We can sub 2 into 1. And how would that look? Well, M2A is just equal to force of 1 on 2. It's the same thing as we had up here. But now we know the force of 2 on 3, which we have right here. We're going to replace this with this right here. We want to put a negative, and then we're going to put the brackets M3A. And we're just going to distribute this negative sign inside. So with M2A is equal to force of 1 on 2 minus mass 3 times the acceleration. Now, let's keep working our way up. So I'm going to rewrite this here. M2A is equal to F1 on 2 minus M3A. So now that we have this, we can keep working. And we know that the force of 1 on 2, the force of 1 on 2 is equal to the force of 2 on 1. And if we look here, we have the force of 2 on 1 here. So how is that useful to us? We have the force of 2 on 1 also here. So how is that useful, and how can we use that, right? Well, we can rearrange this equation that we just made to solve for a force 1 on 2. How are we going to do that? We can just add M3A to the other side. So you're left with M2A plus M3A is just equal to the force of 1 on 2. Now we can label this as equation 3. Label this as equation 4. Sub 3 into 4. So now we can continue. So we can go M1A, so we just rewrite this equation that we have here. So M1A is equal to the force applied minus, then put our brackets, M2A plus M3A. Again, if you're confused why we did that, the force of 1 on 2, we have that here. We just solved for it. We rearranged this equation here, solve for the force of 1 on 2. Now that we have this, the force of 1 on 2, remember, action-reaction pairs are equal to each other. So the force of 1 on 2 is equal to the force of 2 on 1. So we can just sub in 1 on 2 right here for 2 on 1 here. And now that we have these brackets, we're going to distribute this negative sign inside. So M1A is equal to FA minus M2A minus M3A. Now we want to get all the accelerations, because we're looking for acceleration again. We want to get all the accelerations by themselves, right? Because that's what we're really looking for at the end of the day. So let's add all the accelerations to the left side. M2A plus M3A. Now you have M1A plus M2A plus M3A is equal to the force applied. Now that we have all the acceleration on the same side, what can we do? Well, we can just common factor out the acceleration. And now you're left with M1 plus m2 plus m3. Why do we common factor? Well, there's an acceleration in every single term, right? And that's just a constant. Just like if you had ax plus b, pardon me, plus bx plus cx. Well, you have a x in every term. You can just remove this x and you're left with a plus b plus c. That's the same concept we applied right here. So now that you common factored it out, you're left with just equals to fa. Now we want to, again, isolate for the acceleration, so we can just divide by everything in the brackets. So the acceleration is just equal to the force applied divided by m1 plus m2 plus m3. And now you have your acceleration. Now if you want, you can go ahead and solve. This is just all plugging in numbers. So A is just equal to 120 newtons, and then divide that by 12 plus 11 plus 7. So 12 kilograms plus 11 kilograms plus 7 kilograms. And you will get 120 divided by 12 plus 11 plus 7. So you end up just getting the acceleration is equal to 4 meters per second squared. That's your answer for this. Now that you have this, if you're ever, like in part B here, it says calculate the magnitude of the tension of the rope. It doesn't really specify which rope, but let's say if we said rope A. If you want to find the tension on this rope right here, that's pretty easy now, because the tension, again, remember, we have it here. The tension is just the force of 1 on the force, because this is rope. This rope right here is going to be the force of 3 on 2, which is equal to the force of 2 on 3. And now because we have the acceleration, we can just go back here to our old formula. This one right here. The M3A is equal to the force of 2 on 3. Well, now we just plug in our acceleration, multiply that with the mass, and we got the tension in that rope. But that's all for this video. I hope you enjoyed. And just some key concepts to remember here is we have to always draw full body diagrams. And really what this forces unit about is just about rearranging and plugging in different formulas to at last just get really our acceleration. So really you just have to work through this process, and after you work through it, you should be able to just isolate for whatever you're looking for, but you just have to keep going, really. That's all. I hope you enjoyed the video, and remember, physics rocks.